Hi, welcome to the Alkene Edition playlist in organic chemistry. I'm Kevin Tokoph. Make sure to like this video, subscribe to the channel if you like it. In this video, we're going to cover a reaction in alkene additions known as halogenation or alkene halogenation. Now, before we get started on this, I just wanted to say something just from a practical perspective. Out of all the reactions that you're going to see in this chapter, this really is one of the least useful alkene additions. You can see here that I'm going to be making a dihalide. Unless you're making a dihalide, or there is one reason you can use this is to make some kind of alkynes in some cases. Unless you're doing that, there really is not a whole lot of uses for this reaction. If you're going to do synthesis, sometimes they'll have synthesis on some of the later exams. You'll find this is one of the reactions that you tend to use the least. It's not really useful as much as some of the other ones like catalytic hydrogenation, acid catalyzed hydration, hydrohalogenation, and then hydroboration oxidations, things like that. It's not really as useful, okay? But you still need to learn it because there's another type of related reaction that we're going to do in the next video that uses the same logic, and it's actually significantly more useful. In fact, just to give you a foreshadowing, it's going to be something called halohydrin formation, and that type of reaction proceeds by the exact same mechanism for the most part as this one, and they actually use that reaction to make certain synthetic steroids that they can use in things like different steroid drugs. Okay, but let's go into the reaction. So in this one, I obviously have to have an alkene. Okay, so here's just the simplest alkene. What they found is that if you put in a halogen, okay, so molecular chlorine, chlorine and bromine in general, okay, then what's going to happen is the chlorine atoms themselves are going to add across the double bond. See this if I was to look at this, say, oops, let me get my brush, okay, and get the right brush. There's different brushes on paintbrush. If I were to get the chlorine molecule like this, say the other chlorine was the blue one, then what would happen is one of the chlorines is going to add to this carbon, say that's this one, but the other chlorine is actually going to add to the other carbon of the double bond, and you see that one right there. Okay? But it turns out it's not just as simple as that. A lot of the reactions that we've seen thus far, such as catalytic hydrogenation and things like that, they're what we call syn additions. Okay, a syn addition is a type of addition where both of the added groups, one could be a hydrogen, the other could be an alcohol, whatever, they add on the same side of the double bond. However, halogenation and then ultimately halohydrin formation, this is an example of something called an anti-addition, meaning that the two groups, which in this case are just two of the same halogens, they're actually going to add on opposite sides of the double bond. Okay? So let me just call this a generic over here. This is going to be R1, and let's assume for a minute that's a different R2. When I add chlorine or another halogen molecule to this double bond, notice that I could have one of them adding to this carbon, and I could also have the other one adding to this carbon, and that's what happens. But notice I actually get two products right here. Okay, I get two of them. Notice that in this left example, this first molecule, notice that the chlorine that adds on the left, the one closest to R1, okay, that chlorine is on a wedge, okay, and because it's an anti-addition, the other one therefore is going to be on a dash, okay. But when we look at the mechanism, we'll see why that it can be the opposite case. The one on the left, the one on this red carbon closest to R1, can actually add on a dash, and that means the other one's going to add on a wedge. When we look at the mechanism of this, we'll start to understand why that is. And this is actually one of the more intuitive mechanisms that we have in alkene additions. So here's another example of this. Okay. Ultimately, what we're going to have here is you're going to put this. We're going to put this alkene right here. This is just a generic reaction. But we can also use bromine, molecular bromine, excuse me. So if I have bromine atom right there, and then another bromine atom right here, well then one of them, say the red one, it can add to this carbon, and you do see it right there in both cases. The other bromine, which is the blue one, can add to the other carbon, in which case you see it there in blue that I circled. And again, just like in the case of chlorine addition, okay, one of these bromines, say the red one, can add on a dash, in which case the other one has to add on a wedge. But if the bromine that's red adds on a wedge, then by default the other one has to add on a dash. This is a stereoselective reaction, and it's specifically anti-addition. So if you were to see both of these, say, on a wedge or both on a dash, that product is absolutely not observed at all. Okay, it has to be where these are on opposite bonds. One has to be on a wedge, the other a dash, or a dash and a wedge. Okay. Now, notice I've only done chlorine and bromine. Okay. When I do this addition with chlorine, it's not just simply called halogenation. It's actually given this name. It's called chlorination. Okay, chlorination is the specific term for this kind of halogenation reaction. This one I'm using bromine, so you could guess it's called a bromination reaction. Okay, it's bromination. Okay, and that's using bromine on the alkene. So a very generic way to put this reaction is like this. I have two R groups. Here is my alkene right there. And I'm going to use this thing called XX, or sometimes you'll see it written as X2, just an abbreviated form. X is just a generic symbol for a halogen, any atom that's a halogen. But in this case, you can't just use any halogen, okay? The halogen you use has to be chlorine or bromine. So you're either basically going to use Cl2 or Br2. The halogen you use actually cannot be fluorine, and it cannot be iodine. Okay, let's see why that is. Okay, basically, out of all of these halogens right here, first of all, astatine is out. Astatine is radioactive, and it actually tends to decay before it can really be used in any reaction, so it's really not useful for anything. Fluorine is actually significantly too reactive, and so when you use it, it's basically explosive. Too reactive, it can destroy the whole molecule, and you won't even get an addition. So fluorine's out for that reason. And then iodine is also out because for reasons that have to do with the size of the iodine and orbital overlap. Iodine is basically so slow, the reaction is so slow that it's not useful by any means. So for those reasons, you're only going to use chlorine and bromine for this. Okay? So now that hopefully you understand what we can do here, let's go ahead and take a look at the mechanism and understand perhaps why this is an anti-addition. All right, so let's take a look at the mechanism here. And hopefully when we see this, we're going to get a more intuitive understanding of why anti-addition products are the only products that are observed when we halogenate a double bond. Okay, so this molecule that I have right here, this is cyclopentene. Okay, now I'm looking at this. Now technically, I mean, it's not completely flat, of course, because these are, sp3 carbons, but for the most part, I'm just viewing it flat, like on the table. But what I'm going to do is, what I want to do to make it really intuitive what's happening is I want to take this molecule and basically along an axis like this, I just want to rotate it 90 degrees basically to where I'm now kind of looking at the molecule almost as if it was on its side. Okay, something like that. So here's my alkene right here. Now, I'm going to do this mechanism with bromine. Okay, so I'm going to brominate the double bond. Okay, so what have we seen so far for reagents that we use? Okay, well, number one, we've seen hydrochloric acid. That's one of them. We use that to hydrohalogenate. Remember, hydrohalogenation different than halogenation. What else have we seen? Maybe we've seen hydronium, right? Okay, we've seen hydronium, something like that, and things like that. Okay. But what's the unique feature of both of these and things like them? Well, we have here a pretty substantial dipole moment, and it's even larger in this molecule right there, hydronium. Okay, so we have a bond where electron density is being pulled towards one side or the other in a bond. Okay, the dipole moment's very strong in a hydrogen-oxygen bond because most of the electron density is going towards the oxygen. Okay. And so we would say that in general, these two molecules are polar because they have a pretty substantial and significant dipole moment. But then take a look at this molecule over here. Then let's take a look at molecular bromine, right? Take a look at this. Well, you take one look at that, okay? Remember, bromine atoms are the same bromine, okay? Well, every atom has some degree of electronegativity. That's the ability to pull electron density of an adjacent atom towards its own nucleus, okay? So there's an electronegativity that's going to pull the electrons from this bromine towards the one on the right, but then there's another one that's going to do the same thing in the opposite direction for this bromine, but it's going to be in the opposite direction. But notice, the bromines are exactly equal atoms, okay? It's just a linear molecule, so when you add these two dipole vectors, you get 0, meaning that technically, if you took bromine, one molecule, and just put it isolated in a vacuum, there would be absolutely no dipole, and we would say it's perfectly nonpolar for all intents and purposes. And in general, bromine is nonpolar. It's not usually soluble in water. It's nonpolar, things like that. Okay. So one of the things to realize about this is that double bonds, if I view this double bond as sort of being flat like this, double bonds actually have these p orbitals like this. Okay, they have a p orbital like this, and these are regions of very high electron density. So if I look at this bromine atom, the one that's proximal to cyclopentene, okay, bromine, you could imagine, also has an electron cloud, right? Electrons in it. Well, remember, this p orbital of both of these carbons right here from the double bond is electron density. This is very high electron density. Well, if I put this double bond in proximity to the bromine, then the electrons in the electron cloud are no longer symmetric. Okay, the electrons are going to be pushed more towards this side, the other bromine atom, which means that if the electrons are moving towards the blue one, this one develops a partial negative, and if the electrons are moving away from the proximal bromine, the red one, it develops a partial positive charge. And this is the concept that you probably learned about in general chemistry, where you talked about London dispersion forces. It's very similar to that, and it's specifically a type of polarization. So polarization is loosely defined as the ability of one molecule to distort the electron cloud composition of a nearby atom or molecule. So the electron density of this pi bond is able to distort the electron cloud of this bromine, and that makes this bromine slightly electropositive or electrophilic, which is going to allow these pi electrons to attack this bromine. Now, here's where I want you to pay very close attention. Remember, these bromines have lone pairs on them, okay? Now, there's going to be a very strange type of mechanism that you haven't really seen. It's going to involve things that you've seen, but it's just going to be a little bit weird. So first of all, the pi bond here is going to attack this bromine. It's able to do it because there's high electron density, and the bromine right here is electropositive. Now, what that does is it causes loss of bromide over here, loss of the blue bromide, and you actually can see it. I have it right here. But at the same time, one of these lone pairs on this bromine can actually come and attack, we're going to say, on this carbon right there. Okay? What does that do? Well, you can sort of think of it as this right orbital is making a bond with this bromine, and then the lone pair on this bromine is making a bond with the left orbital. So what I get is this structure right here. This is called a bromonium intermediate. Okay, and it's sort of similar to an epoxide. If you don't know what an epoxide is, this is an epoxide right there. Okay, an epoxide is a three-membered ring where two of the atoms are carbons and the other one's an oxygen. So this one's sort of similar, except the oxygen is replaced with a bromine. If I had done the mechanism with chlorine, then it would be a chlorine here, and then you'd call that a chloronium ion. Okay, so kind of the same thing. The mechanism would be exactly the same if it was chlorine. Okay, now just like an epoxide, it's a three-membered ring. It has a lot of angle strain and ring strain, so it's a very reactive intermediate. So let's see what happens. Well, what can happen is the bromide that I generate can actually attack one of these carbons. I'm going to initially draw it attacking the right carbon, which is going to cause this to leave, and so that means that this bromine over here, the red one, is going to be pointing up, and then the bromine attacked from the bottom, it's going to be the blue one, and it's going to be pointing down from the ring. Okay? Why does this happen? Well, Because there's already a high degree of electron density right here in these bonds right there, okay, though that electron density is actually repelling the bromide from attacking from the top, okay? So as a result, because of also some sterics as well, the bromine has to attack from the opposite side of the ring or the double bond that the other bromonium is occupying. Okay, so if the bromonium we draw on the top, and we could also draw it on the bottom, but if the bromonium's on the top, the other bromide has to attack from the bottom. It cannot attack from the top due to electronic repulsion. Okay, now if the bromide attacks this side, then obviously the blue bromide is going to be on the bottom and the red one's going to be on the top. But suppose, for instance, I have the opposite case. What if instead the bromide attacks this position, the left one? Well, it's basically identical. It attacks that position and you get loss of a leaving group, although this bromine is still attached to the right carbon. So what do I get? Well, the red bromide is now going to be right here. And then the blue one attacked the left side from the bottom, so the blue one is going to be here on the left side, okay? And so what does this mean? Well, notice, on opposite sides of where the double bond was, the bromines, they're on opposite sides, okay? So one of them is going up, the other is going down, okay? And in this case, the first one's going down, the second one's going up. And that is the characteristic of the anti-type addition. This is an anti-addition, okay? The syn product is not observed here, okay? So hopefully that gives you a little bit of an intuition as to why they add on opposite sides. Now, normally we don't obviously draw molecules like this. So how is this useful to us when we're actually doing, predict the products kind of things? Well, the way it's useful to us is that if they're anti in nature, that means that one of them is going to be on a wedge and the other has to be on a dash. Let's look at a very good technique that I've explored in previous videos explaining how you predict the products. So the thing I always do, and if you want more information on this, I have a whole video explaining this technique, okay? You draw a dotted line right through the double bond, okay? And we're going to do a few examples of this, so hopefully it becomes less foreign to you. All I'm going to do is I'm going to say, I'm going to pick everything on the bottom side of this double bond to remain the same, or I'm going to say remain in the plane. Remember, if it's not on a wedge or a dash, meaning it's just on a solid line, that means it's in the plane of the screen. So that's what I'm going to do. I'm just going to redraw everything below that in the plane. Then what I'm going to do is I'm going to take the two bromines, I'm going to do those in blue, and I'm going to put one here on a wedge, and then since it's anti, I'm going to put the other here on a dash. That implies that this group over here that was already there, that one has to be on the dash. Remember, there's also a hydrogen there, and so then that has to be on a wedge, okay? And that's one product right there. But remember, you can also, remember I showed you that you can get the nucleophile attacking from either side here, okay? So that means I can actually get another product, and so what I'm going to do is the same thing. Everything below this dotted line, I'm just going to redraw, okay? But instead, the bromine I put on the left, now I'm just going to put it on a dash. And then the other one automatically, therefore, since it's anti, has to go on a wedge. Then I'm just going to fill in what's already there. This methyl, since this is a dash, this has to be on a wedge. Then this hydrogen, because this is a wedge, the hydrogen has to be on a dash. Okay, so hopefully that makes sense. And those are our two products. Okay, let's look at another example. Here, okay, I'm going to again draw the dotted line right through that double bond. Okay, hopefully they'll show up. Actually, there we go. Okay, let's do this again. Let's pick down here. Let's pick everything there to remain in the plane. Okay, remain the same. So all I'm going to do is I'm just going to draw this. Okay. And actually, one thing I just want to remind you, again, this technique is not something they usually teach you, but if you watch the video explaining it, remember this technique for predicting the products. It doesn't matter which side you pick to remain the same. I could have picked the top side here to remain the same and put wedges and dashes on the bottom, and it would actually be the same thing. You could show that you can rotate the molecules such that it would give you exactly the same product. Okay. Here is my isopropyl group. Okay. And here's a methyl group over here. I'm adding chlorine this time, right? So what I'm going to do is I'm going to put a chlorine here on a wedge. And then that means because it's anti, this has to be a dash. Then I'm going to go in and fill everything else in. Here's an isopropyl right here. So this obviously has to be on the dash. Here's a methyl. So this is a dash. This obviously the methyl has to be on a wedge, right? So hopefully that makes sense. But remember, again, I can get the other product. So let me just keep everything on the bottom there the same, right? I drew the wedge chlorine on the left here. So that means on the left this time it has to be a dash. And then over here, this chlorine would have to be on a wedge, right? So hopefully it's starting to make sense. The isopropyl group here, I drew them in blue there, sorry. But the isopropyl group here would therefore have to be on a wedge. And then here the methyl group would therefore have to be on a dash, okay? Those are your two products there. So hopefully this is starting to make sense. Here, I have another addition reaction, another double bond. I'm going to draw a dotted line right through that. Sorry about that. That's my cat meowing. So then for instance, let's just pick everything on the top to remain the same. Okay, in the plane. And I'm just going to draw that. Okay. Okay, there's everything remaining the same. I'm chlorinating. Okay, so again, let me just draw wedge chlorine there, right, on this carbon. Then this carbon, I'm going to draw the dash chlorine because it's anti. Then let me pick, this is a wedge, so that means this phenyl group has to be on a dash, and then on a wedge here, you have to put that hydrogen. And that's one product. And again, remember, I can get another product. Okay, so I'm keeping everything on the top of that dotted line the same. Now I'm going to put the chlorines in. So this one was on a wedge here. That means the left one has to be a dash this time. And then the one on the right has to be a wedge. Okay? Then that means the phenyl group on the left here, therefore, would have to be a wedge. All right. Okay, let's see. And that's an ugly phenyl group, but you get the idea. And then because the chlorine here is a wedge, that means the hydrogen has to be on a dash. And those are the products of chlorination of that alkene. Okay? Let's look at one other example. Okay? So let's do this. All right. Here we go. I'm going to draw a dotted line right through that alkene. All right? And we picked the top this time. We did 2 on the bottom. Let's pick everything on the top to be the same this time. Okay, so we get 2 and 2. All right, so again, everything on the top's in the plane. I'm going to just draw everything like that. I'm going to leave the rest of the cyclopentane alone, and you'll see why in a minute. But now I'm going to add the chlorines in. Or actually, this is bromine this time. Bromine, okay. This bromine on the left, I'm just going to draw on a wedge, and therefore the other one, because it's anti, has to go on a dash, right? This isopropyl down here, this is a wedge bromine, so the isopropyl has to be a dash, right? And then the rest of this cyclopentane sort of thing right here would have to be a wedge right there, and then I'm just going to kind of fill it in like that. Okay? Let's look at the other product, kind of keep everything here the same, right? All right, there we go. Let's look at the bromines. So the bromine on the left, here it was a wedge. So now to get the other one, it has to be a dash. The one on the right was a dash. Now you have to put it on a wedge. Okay, let's fill in the other things that were already there. Here the isopropyl is on a dash. So by default, this one has to be a wedge. And then here, this ring, the bottom part of it was on a wedge. Now I'm going to put it on a dash, okay? And those are my 2 products of bromination, okay? So hopefully that makes a little bit of sense, okay? One thing I just want to also tell you about, particularly bromination, you can do this with chlorination, but it's arguably significantly more useful for chlorination. So let me give you this. Whenever you do these reactions where you're doing specifically an alkene addition, I don't care if you're doing it with chlorine or bromine. Generally, when you do this, And it might seem a little trivial, but you don't want light shining on it, okay? Particularly high energy light, and to be specific, UV light, okay? So it's not to say you generally have to do these in a dark room, but you just don't want UV light shining on it. And here's actually why that is, okay? If I look, I'm going to look specifically at bromine, molecular bromine that is. There's something that actually happens if you shine UV light on it. Okay, so I'm going to put some UV light on this. Okay, now we haven't done any reactions or mechanisms that really involve this, so I am jumping a little bit ahead, but this is just really a warning for you. Okay, because you are going to see this in a couple chapters. There's a concept called radicals. A radical is a free electron. It's an electron that's in an orbital all by itself. Okay. And a lot of times if you have unstable molecules like molecular bromine, it's pretty unstable, and you provide energy in the form of UV light, which is pretty high energy molecule, you can cause this molecule to split apart. Okay? So remember, normally when you're doing mechanistic steps so far, you usually drew an arrow like that. Okay? Remember what that actually symbolizes is that symbolizes 2 electrons moving. Okay? In that arrow, 2 electrons are moving. But actually, if you actually wanted to signify 1 electron moving, you take one of these hooks off of the arrow and you just draw it like this. This is what we call a fish hook arrow, and it's used for radical mechanisms. So just keep in mind, remember this, that this bond is actually 2 electrons, right? And then, of course, the bromine atoms each have 3 lone pairs. Now, what can happen is one of these electrons can actually move onto this bromine, and the other one can move onto this one. So 1 electron's moving in each direction, so you use a fishhook arrow. That's going to basically generate 2 atomic bromine radicals. Okay, so I'm going to draw this one in red, although one of them is blue, but you get the idea. This is what we call atomic bromine, and it's a radical. This is a free radical, but mostly in organic you just term them radicals. Okay? The reason this is important is because if you are using bromine and you have light shining on it, that means you're going to have some amount of this. And this radical does a completely different reaction than halogenation, okay, on an alkene. This halogenation is an addition reaction, and it proceeds by the mechanism that we showed here. If you were to generate radicals, these are very reactive, you're going to get a whole host of other products. And so for that reason, you really don't want UV light shining on your reaction mixture, because then you're going to get radical products. And in a couple playlists when we cover radical chemistry, we're going to understand why that is. So just know you want to do this with as little UV light as possible to get the desired product, okay, for either chlorination or bromination. So hopefully this video made a little bit of sense. In the next video, we're going to cover something called halohydrin formation, a very similar reaction to this. See you in the next video.